Okay, we're going to be dealing with 18.1 vector fields. And this is really quite interesting. I would encourage you to read the section of vector fields because this is really an interesting way to think about movement, okay, and how things move throughout, say, water, for instance, okay? So I would encourage you to read about vector fields, because this is just going to give you just a snapshot of what you're supposed to do. But it's really quite interesting to see all of the different applications. So I would read the section before where it talks about kind of the outline for chapter 18, because it's really quite fascinating. So let's talk about what a vector field is. So a vector field in 3 dimensions is a function f, whose domain is a subset of the reals, so R3, and whose range is a subset of V3. Okay? If your X, Y, Z is in the domain D, then you have F of X, Y, Z is equal to M of X, Y, Z I hat plus N of X, Y, Z J hat plus P of X, Y, Z K hat. And essentially what this means is there's a vector. Think about this. It's a vector assigned to every point. So to every point. Okay. And this is how a vector moves through, say, solids, liquids, and gases. So solids, liquids, and gases. So again, does it move in kind of a circular pattern? Is it doing this? Are these vectors doing this? Are they moving out from a point? See how I have all these little vectors? You know, maybe it's moving out from a point. Maybe it's all moving in a similar direction. Okay. So in this section, you're going to want to calculate lots of different vectors to kind of see what the movement looks like. Now here our M, our N, and our P are scalars. So this is where our M, our N, and our P are scalars. Okay, so if we have 2 dimensions, so in 2 dimensions, our F of XY would be given by M of XY I hat plus N of XY J hat. Okay, so let's let U, now remember U is our unit vector, equal our vector R times 1 over the magnitude of our R, and the same direction as our R, which is equal to X I hat plus Y J hat plus Z K hat. Okay, this would obviously be in 3 dimensions. 2 dimensions would just be your x, y, I hat, or x, I hat plus y, j hat. Again, this is your position vector. So this is your position vector. And this was our unit vector, Okay, F is an inverse square field. So inverse square field. If, sorry, I forgot to write if. Our F of x, y, z is equal to c over the magnitude of our r, quantity squared, times our u, which is equal to c over the magnitude of our r, magnitude of our r cubed times our r, okay, where c is a scalar. So let's talk about that real quick. Okay, so if this was essentially c times our unit vector, well, our unit vector is r over 1 over the magnitude of r. So this would give us r over the magnitude of r times that squared. So that's why it would be cubed. Or you can just multiply it by the unit vector, okay? Because the math is still the same. So it's c times our unit vector, which is r over the magnitude of r times 1 over our r squared, which is what gives us that r over r cubed, or I'm sorry, the magnitude of our r cubed times whatever that scalar is. Okay, so that's just the math. Okay, all right, so let's look at our vector field. Our vector field, we'll call this F, is what we call conservative. Okay, conservative if F of our x, y, z is equal to, okay, remember this, F of x, y, z, okay? Remember this from chapter 17, this is our gradient, okay? So every inverse square vector field is conservative, okay? So essentially what this is saying is every inverse square vector field is conservative. And then we have this concept of the curl of our function, which is our gradient cross our vector field F, which is given by the partial of P with respect to Y minus the partial of N with respect to Z. And that's our I hat plus the partial of M with respect to Z minus the partial of P with respect to X. And that's J hat plus the partial of N with respect to X minus the partial of M with respect to Y. And that's our K hat. Okay. And just remember, this would be I hat, J hat, K hat. In case you have forgotten, this would be the partial with respect to X, the partial with respect to Y, and this would be the partial with respect to Z. And this would be our M, our N, and our P. Okay. So that's really what's happening there. So it's that vector. Okay. I hat, J hat, K hat. And this would be if we're solving for our I, this would be partial of P with respect to Y minus the partial of N with respect to Z. So here's that. That's that first one for I hat. Because remember, when you're solving for I hat, you're dealing with this times this minus that times that. Okay, so that's where that partial of P with respect to Y, so the partial of P with respect to Y minus the partial of N with respect to Z comes in. Okay, and that's our I hat. Same with J hat and K hat. Again, this is nothing new. You've been dealing with cross products for a while. Okay, so that's the curl of F. The divergence of F is equal to the gradient dot our vector field, okay, which is equal to the partial of M with respect to X plus the partial of N with respect to Y plus the partial of P with respect to Z. Okay, so that's the divergence. And the curl, I was going to say curl of, the curl F will be a vector of divergence F. Okay. All right. So if you look on page 971, we have 1 through 4 and 11 through 18. Okay. For these, look on page 865 for, I'm sorry, 965. I don't know where I got 865. 965 for an example. Okay. This is where I like to tell everyone for those first few problems, you need to solve a lot of these little vectors. Okay. The vectors, if you take some graph paper, you're definitely going to want to do this on graph paper. Okay. And just to give you an idea for problem number 1, I'll just get you started with problem number 1. It's going to be F of XY is equal to I hat, I'm sorry, XI hat minus YJ hat. Okay. So I would want to say find F of 1, 1. Okay. So what I would do is I would plug in 1 in for X. So I'd have 1 I hat and then minus 1 J hat. And I would go over to my graph paper and I would graph that point. I hat minus 1 J hat. And then say F of 0, 1. Well, that's just going to give me negative J hat. Okay. And then F of 1, 0. And that's going to give me I hat. Okay. So you're going to find a lot of these. Okay. 1, 1, 0, 1, 1, 2, 2, 2, 3, 2, 2, negative 2, 4, 2, 5, 3. I mean, just plug in different values as you're going through to be able to graph this. And what you're looking for is you don't just want to have, I'm not drawing this example for problem number 1 because I want you guys to figure it out. But say you just solved for 4 of these, you don't really know what's happening. Maybe as this gets out here, it starts to curve in this direction, okay? But you have to draw a bunch of them to kind of see what's happening. Okay. So maybe as we expand this out, we're going to see that from the beginning, it starts to come out and then it starts to curve in this direction. Okay. So you're going to have lots of vectors. These are not hard to calculate and they're not hard to draw, but you need to draw a bunch of them. And if you look in the back of the book for the answer to say number 1, you'll definitely see a pattern. So this is where I would say you're going to need at least maybe 40 points on this vector to kind of see what's happening, okay? And you may need more, you may not need that many, but you want to have enough to where you start seeing what the pattern is and what the overarching vector field looks like, okay? Because just having maybe 5 or 10 of them is not going to be enough, okay? So good luck, but again, you're going to need graph paper for these. So graph paper for these problems, okay? All right, there we go.